Hello dear students, how are you? Good morning. Had your breakfast? Fine. You have more energy today to listen the lecture. Okay. Today in the hydraulic turbines itself, we will study unit quantities. In the last class we have seen specific speed. What is the use of specific speed? Based on the value of specific speed, we can classify the turbine. Is it not? We have learned it. In the similar way, unit quantities are used in order to understand or in order to compare the performance characteristics of 2 or 3 different turbines of same type. That is important. Same type, but 2 to 3 turbines are working together at different parameters or under different conditions, under prevailing conditions. For example, different heads with which these 2 or 3 of same type of turbines are working. In order to compare them, we want unit quantities, right? So we will see unit quantities. This is useful for understanding the performance of turbine. Turbines are often required to work under varying conditions of head, speed, output and gate opening. It is not quite possible to maintain the same speed, same head, same output and gate opening throughout all the time. As such, in order to predict their behavior, it is very essential to study the performance of the turbines under the varying conditions. Head, speed, power and gate opening. These variable conditions can be developed only for laboratory turbines or those in the test plant, and are otherwise it is uncommon. What is the meaning of this? The variable conditions, these variable conditions, head, speed, power, gate opening, can be developed only for laboratory turbines or if at all in the test plants, but are otherwise uncommon. To facilitate comparison between the performances of the turbines of the same type, that is important. I have already said at the beginning, same type but having different outputs and speeds and working under different heads, it is often convenient to express the test results in terms of certain unit quantities. Therefore, these quantities are known as unit quantities. What is meant by unit quantities? These are the quantities by means of which we can understand the performance of different turbines working under different conditions, wherein turbines are of same type. Therefore, the conditions of the turbine working under unit head are such that the efficiency of the turbine is remain unaffected. Under any circumstances, the efficiency of the turbine will not be altered or affected. In short, utility unit, say speed, discharge or power, is that quantity which is obtained when the turbine is working under unit head. Condition is that efficiency should be constant or unaffected. Okay? Now, we will see unit speed NU. What is the expression and how it can be brought? Speed of turbine working under unit head. You have to make a bold statement. that speed of turbine working under unit head. Let N is equal to speed of the turbine under head H meter. H is head under which the turbine is working. U is the tangential velocity. We know the formula for tangential velocity. U is equal to pi dn by 60, which implies U is proportional to N, because for a given turbine D remains constant. Also, U is equal to Ku. Also, U is equal to Ku under the root 2GH. U is proportional to root H. Therefore, N is proportional to root H. Therefore, N is equal to K1 into root H, where K1 is constant of proportionality, where K suffix U is speed ratio. Let us call this equation as 1. When H is equal to 1 meter, that is unit head, we know N is equal to Nu, that is unit speed. As we did in case of specific speed, when the turbine is working under unit head H, produces a power of 1 kilowatt, then speed N is considered as specific speed. In the same way, when turbine is working under a head of 1 meter, speed will be considered as unit speed, denoted by N suffix U. Nu is equal to K1 into root 1, because H is equal to 1. Therefore, Nu is equal to K1. Hence, equation 1 becomes N is equal to Nu into root H. From this, it is possible to get the equation or expression for Nu as N upon root H. Nu is equal to N divided by root H. Similarly, we can find Qu is equal to Q upon root H. How? Here also we have to make bold statement. Discharge passing through the turbine working under unit head. Let Q be the discharge passing through the turbine under head H meter, which is equal to area of flow into velocity. Now velocity we know Cv multiplied by root 2GH, where Cv is coefficient of velocity. You can assume it as 0.95. You can assume it as 0.95 value of Cv. Then V is proportional to root H. For a given turbine, D or area of flow is constant. Therefore, Q is proportional to root H, which gives Q is equal to K2 into root H. Here K2 is taken as the constant of variation. Since we are considering 3 parameters simultaneously for the turbine, constant of proportionality, we are denoting it as K1, K2, K3 and so on. When H is equal to 1 meter, that is unit head, Q is equal to Qu, unit discharge. Therefore, Qu is equal to K2 into root 1. Therefore, Ku is equal to K2. Hence, Q is equal to Qu root H, from which Qu is equal to Q upon root H. Okay. Similarly, unit power Pu is found to be equal to P divided by H to the power of 3 by 2. Here also, we have to make a statement: power output of turbine working under unit head. Let P be the power developed by the turbine under head H meter. Here head is effective or net head in each and every case. We know efficiency, overall efficiency is equal to power divided by rho G QH, which gives us P is equal to overall efficiency multiplied by rho G QH. Also, P is proportional to Q into H, because efficiency and rho G are constant. Therefore, P is proportional to root H multiplied by H. That is nothing but P is proportional to H to the power of 3 by 2, which implies P is equal to K3. Remove the proportionality constant. Put the constant of variation. Constant of proportionality K3. P is equal to K3 multiplied by H to the power of 3 by 2. Let us call this equation as 1. When H is equal to 1 meter, that is unit head, we know that P is equal to Pu. Therefore, Pu is equal to K3 root 1. Pu is equal to K3. Hence, P is equal to Pu multiplied by H to the power of 3 by 2. From which we can get unit power P is equal to P divided by H to the power of 3 by 2. Now, summary of unit quantities. Before going to the summary, use, let us know. If a turbine is working under different heads, the behavior of the turbine can be easily known from the values of unit quantities as under. Let H1, H2, H3, etc. heads under which a turbine works. N1, N2, etc. corresponding speeds. Q1, Q2, Q3, etc. corresponding discharges. P1, P2 corresponding powers developed. Then using unit quantities equations, we obtain Nu is equal to N1 upon root H1 is equal to N2 upon root H2 equal to N3 upon root H3 equal to so on. Similarly, Pu is equal to P1 upon H1 to the power of 3 by 2 is equal to P2 upon H2 to the power of 3 by 2, etc. Similarly, unit discharge Qu is equal to Q1 upon root H1 and Q2 is Q2 upon root H2. Means we can find out what is Q2 if the turbine is working under head H2 provided we are knowing H1 Q1, right? That is the basic use of unit quantities. Unit quantities use is in order to find out the speed of another turbine which is working under another head, power and discharge. Suppose you are having 2-3 turbines in your establishment, for example, of same type of course. All these 3 turbines cannot work under same head, maybe or may not, but may not be working under same head is the prevailing condition. In that case, if you know H1, Q1, P1, N1, etc., then when those turbines are working under different heads or different speeds, then the rest of the parameter can be evaluated. If we see one example, we will come to know how this utility of unit quantities may be used. A turbine is to operate under a head of 25 meter, means capital H is equal to net head 25 meter at 200 rpm. Say N1 is equal to 200 rpm, H1 is equal to 25 meter. The discharge Q1 9 meter cube per second. If the efficiency is 90%, determine the performance of the turbine under a head of 20 meter. Means here H2 must be 20 meter. H1 is given 25 meter. N1 given 200 rpm. Q1 is given 9 meter cube per second. Efficiency 90% in all the cases. That is the basic concept of unit quantities. Yeah, efficiency of the turbines should not be get affected, right? Unaffected means it should not be get affected. Performance of turbine under H2 is equal to 20 meter. What is N2? What is Q2? What is P2? Is the question. P1 is, we know the equation P1 is equal to overall efficiency multiplied by rho G QH, so that you can calculate, because rho is taken as 100 kg per meter cube, G is 9.81 meters per second squared, then efficiency is given 90% means 0.9, Q is 9 meter cube per second discharge, H1 head 25 meter. Therefore, the power P1 is equal to, here it should have been H1 Q1 1986.5 kilowatt. Now we know the formula Nu is equal to N1 upon root H1 is equal to N2 upon root H2. N1 is known, H1 is known, H2 is given 20 meter, N2 you can find out. N2 you can find out. Therefore, N1 upon root H1 is equal to N2 upon root H2, which implies N2 is equal to N1 root H2 divided by root H1. Substitute the values, you will get 178.88 rpm. Similarly, Q2 is equal to 8.05 meter cube per second, and P2 is equal to 1421.4 kilowatts. Similarly, so many problems are there, right? Even we have uploaded many number of problems which are solved, not in the books. Question paper problems are solved. Such numerical problems around at least 8 to 10 in some units, in some topic 12, 13 question paper problems have been solved and uploaded. Please refer all those from LMS platform. Definitely it will be possible for you to work more and more numerical problems and different types, terminologies which come across in the exam. You will be aware of it so that you can tackle any such numerical problems in the exam. Thank you very much for patient hearing. We will continue in the next class, please. Okay, we will stop for today. Have a good day.